Hello guys, it's Serge here, and today is the 5th episode of Rewriting Physics, where today we'll be covering moles and different molar quantities. In order to start, let's define the amount of substance, which is measured in moles. So, N is the traditional notation for it, and it is measured in moles. So, we will define eta to have units of moles, because N is already unitless in our system. And eta looks like N, that's why I chose it in this case. Now, let's look at molar mass. So molar mass, which is usually symbolized by big M, is small m over N, so mass over number of moles. And so we symbolize it by, well, let's actually look at the units. That's just kilograms per mole. And the symbol that is kilograms per U is mu. So this can already be seen as mu eta. So mu sub the number of moles. And that is 0 eta if we want to be more specific. So now, let us look at the next concept, which is mass concentration. And while this doesn't need moles, it's still useful to look at anyways. So next is mass concentration, usually symbolized by rho, which makes sense because it is mass over volume, so it's just a density. And thus, that is very easily symbolized by mass per volume, per our episode 3. And then I would like to look at molar concentration, which is also called molarity. And molarity is, molarity, which is usually big M, is the number of moles per volume. And again, that's just something per volume that is very easy to symbolize. And then I would like to look at molality, of which I think is also symbolized by big M. Molality is the number of moles per mass. And if we flip this around, we can see that molality and molar mass are just inverses of each other. We can very easily see that this will give us the reciprocal of mu 0 eta. And eta again is the number of moles. Then I would like to look at the mole fraction, of which is also pretty easy to symbolize, considering it's unitless. The mole fraction in our system is just N eta, and the only reason that eta is superscript is because N comes from eta. And the mass fraction is similar. It is a part mass over a whole mass. And so mass fractions are just N for mass. And now I would like to look at specific volume. And specific volume is just volume per mass. Volume per mass, while it can be represented as this, so the reciprocal of mass per volume, you can also symbolize it in a slightly different way. If you look at volume per mass, the units for this would be meters cubed per kilogram, but we can look at this in a slightly different manner. Let's take kilogram squared and multiply this by meters per kilogram cubed. These are equivalent. This is defined as area sub 3 mass. And then I would like to look at chemical potential. So if we scroll down, chemical potential is usually symbolized by mu, as far as I'm aware, and it is the derivative of the Gibbs free energy over, by moles. And if we turn that into our notation, we get the derivative of energy by moles. And that would have units of kilograms times meters squared per second squared mole. We can separate things out and get kilograms times mole per second squared, meters per mole squared. And thus, the chemical potential can be represented by F2 eta. And then I would like to look at heat. While yes, heat just has units of energy, it is its own separate concept. And so I will just consider heat as Q tilde, because Q is already used for heat and charge, so I had to do something there. So heat is Q tilde in this notation. And next, I will also define temperature, which we will define as T tilde. So that is temperature. And then, with that being stated, we can now do entropy and enthalpy. A change in entropy is a change in heat per temperature. And so, in our new notation, that would just be Q tilde per temperature. And we would get units of kilograms times meters squared per second squared Kelvin. And actually, let me switch those. And so if we separate all of the meters out, we can get kilogram Kelvin per second squared, meters per Kelvin squared. And we recognize that as the units for force. So entropy can just be symbolized as F2 T tilde, or F2 temperature. And enthalpy, which I guess I'm just going to do N. And enthalpy is the total heat energy over the number of moles. And the way that was symbolized in my research is delta H over N. But in our notation, we can recognize that as a form of energy per number of moles. And so we find kilograms meters squared per second squared mole. And it is pretty easy to see that that is F2 eta. Just like the chemical potential. With that being said, the last couple of things I would like to look at are atomic mass and particle number. Atomic mass is just a mass, so it can just be symbolized by like M of atom. So atomic mass could just be like M atom. And the number of particles, so particle number, again, that's unitless, so N. Just in particles or something like that. And then something else I wanted to show is vapor density. Vapor density, again, is just mass per volume, so vapor density can just be this again. Doesn't really do much. But with that being said, a summary of today is we've looked through many different molar quantities, whether they relate specifically to moles or just to chemical reactions in general. We have also defined two new concepts. Those would be the heat, well, actually three new concepts. The heat, the temperature, and the number of moles. And again, heat is just joules. Temperature would be Kelvin or Celsius. And number of moles is just molar unit. Now, there's also something I would like to mention that I kind of just passed over last episode and this episode. That is the definition of volume and area when looking at things other than length. So yes, usually we think of area as meters squared, but of course this notation generalizes it, or should I say length squared. But this notation generalizes that. And so an area of a unit is just a unit squared. Volume of a unit is just that unit cubed. And of course, you can always add numbers to that unit. So meters per unit to the n, and meters per unit to the n, and there's our official definition for that. However, of course, you can always just do, for example, this, u meters per u to the n, and the way you do that is just by using epsilon. So it's a little awkward, but it works. As a specific example, let's do, that should not be a 3, that should be an n. As an example, let's do epsilon 3t. That would just be temperature times meters per temperature cubed. Or in other words, those units would just be meters cubed per Kelvin squared. And temperature there should just be Kelvin, actually. Not that that specific case will be useful, but it's nice to know about. So with that being said, this has been Ert, and I will see you next episode. And until then, goodbye and peace.